In this video, we're going to look at the modulo function. So we can write this as mod a comma b. Now it's best seen by example. If we had mod 10 comma 3, it's equivalent to saying 10 divided by 3 is equal to 3 remainder 1. Now the mod function returns the remainder. So the answer to this is 1. Here's another example. Mod 17 comma 5, that's 17 divided by 5 is 3 remainder 2, so the answer is 2. Now, as with most of these mathematical functions, the devil is in the detail. So let's look at these three examples. If we had mod 0 comma b, that would be equivalent to 0 divided by b, which is equal to 0, remainder 0, which is equal to 0. If we had mod a comma 0, then that's equal to a divided by 0. We can't divide by 0, it is undefined, so this is the empty set or undefined. Mod 0 comma 0 is 0 divided by 0, again, which is undefined, so this is the empty set. So we want to write a program in our assembly language that will work out this modulo function. So you can see here it's a simple division and we take the remainder. And we also want to take care of these three conditions as well. Now one other thing before we finish the mathematics is that we are only doing this for integer values which are positive, so greater than or equal to 0. We can work out the modulo function for negative values, but there's a little bit more involved in it. And we don't need it for the moment. If we need it later, we can build it in. So let's go ahead and we'll see how we're going to code this into our assembly language. Now we have our two pieces of code again. We have our calling function on the right and our subroutine on the left. So let's talk through the calling function. We're going to push the two variables a and b onto the stack, and then we're going to jump to the subroutine math_mod. We define math_mod as a position in the ROM where the program starts, and it jumps to that point. So now it's jumped over here to the subroutine. It will run through the subroutine and it will give you an answer in a memory location in the RAM called result. Now after it's done that, it will return back up to the calling function, and the next line in the calling function we will load the result into register R5 just to make it easy for us to see what the answer is, and then the program will end. So that's the calling function. Let's move on to the actual subroutine. Now the first thing that's going to happen in the subroutine is that we're going to be using registers R0 and R1. So we're going to save the original values of R0 and R1 into a couple of memory locations here, R0 temp and R1 temp. And then we're going to pop the values off. So we'll pop off the return address, and then we'll pop off the value b into R1 and a into R0. We'll then go ahead and check and see whether any of the inputs are negative. So we'll compare #0 to R0. We'll jump if a is greater, so that is if 0 is greater than R0, then we know that the value for R0 must be negative. So jump if a is greater than to trap a. So we head down here to the trap a. In that case, it's going to put a value of 2 into our trap. So we know if we get a value 2 in our trap, it's a specific value that's dedicated to this subroutine and this issue. And this issue would be one of the values of the input. In this case, it's going to be the a value would be negative, and we're not allowed that in this function. Now we can go down through the same thing here. we can compare the value 0 with R1, and again we can test and see whether it's negative. If it is negative, again we'll jump down to trap A and we will put in a value of 2. We know that that value is negative. So we aren't able to tell which value actually is negative. We'll just make, it'll come out and we'll just say one of the values is negative. Okay, so we don't actually know which one. We could, if we wanted to, add another trap in, and then we could make another number and we would know whether it was the A value or the B value. So it's up to yourselves. For me, I don't think we really need that. Now, the other option we have here is if the value for B is equal to 0. So if it's equal to 0, then we're going to have a division by 0. Division by 0 is undefined, so it'll go down to trap B, so it'll come down here and it will respond with a value of 3 in the trap, which tells us that we're in this function and we've got a division by 0, and then it will end. Now, whenever it jumps down to the end, you'll see jump to end, jump to end. What it will do is it will reload the original values for R0 and R1 back into those registers before it does the final jump back to the calling function. So those are the values. If there's any errors or if there's any traps, that's what's going to happen. Now, if there aren't any traps, then we're going to simply go through a division. So I've got this division here, div R0, R1. So what it does is it divides R0 by R1 and it puts the result in R0, and the remainder goes into R1. So we can find our remainder here in R1, and what we do is we store that remainder in result, and then we jump to the end again. So when we jump to the end, again it's going to put the values for R0 and R1 back in the original values. And at that point we're going to jump to the return address, so we jump back up here, and again we're going to take the result and put it in register R5. So that's the entirety of the code. What we'll do next is we'll go and we'll load the code up, we'll see it operating, and I will also show you an extra change I made to the circuitry in the ALU in order to generate the remainder here for this division. So we have our calling function here. We're going to put the number 17 in for A and 5 in for B. So it's mod 17, 5. So 17 divided by 5 is 3, remainder 2. So we should get the result of 2, which will be placed in register R5. So let's save that, and we can come in and generate the assembly code for it. So I'll show you that happening here. And that's it, generated the assembly code down here. Now we can load this assembly code in. Now we'll just run through it here. Tick enabled. And it should take only a few seconds, maybe 10 seconds or so to run through. And if it works, we should get a value of 2. So there you go, it has worked. Now I'll show you what happens here if we put in the value of 0, 0, because we know it's going to end up with 0 divided by 0, and it's undefined. And again we'll run through and we'll assemble it. And that's it, generated the assembly language code, and then we'll have to just simulate, reset the simulation, and we'll load up the new code. the new code here. Now, and we'll run through the program again. So this should come up with a trap error. And I have gone through and I've tested all of the possibilities, and they all work. And we've got this trap error 3. So if we wanted to, we could go and look up somewhere in a list somewhere, possibly in Excel, and find trap error 3. Trap error 3 would tell us exactly where the error has occurred. Now let's pause that for the moment, and I will now go in and show you the change that I made to the circuitry in order to get the division algorithm working. So we will head down into the ALU, and I'll make this a little bit bigger for us. Now you can see that we have our divider here. Now previously the remainder here, which comes out the bottom, was just hanging. It wasn't going anywhere. So I have adjusted it, and I've taken the remainder out as well. So we've got a 16-bit value here for the division and another 16-bit value here for the remainder. And you can see here that I've put them in to an extra bit of circuitry which I've built in here. I've just called this REM. So this REM takes the division, takes the remainder, and it also takes the control line. Now that control line just came from the actual decoder at the bottom. So that's the input which comes from the control unit, which chooses which function within the ALU we're going to operate. Now we know we're going to operate the division function here. But what has to happen in this case here now is that we don't just have one output for the division, we now have two. So it means that we need a method of, first of all, choosing the division value and placing it into register R0, and then choosing the remainder value and putting it into register R1. And we can do that by pulsing this line here twice within the microcode. And then we just need a little bit of circuitry here that chooses the first one, the top one on the first pulse, and the second one on the bottom pulse. And in fact, we've already generated a little bit of circuitry that does that for us. And so let's get in here and we'll have a look at this. So this circuitry might look familiar. We used this in the graphics in order to generate the graphics card. So I'll actually show you that. If we get in here, if I head down into the graphics card here, you can see we've actually got this circuitry already built for us. So let's get in and we'll quickly have a look and we'll see that working within the ALU. So all we're going to do is have our control line here, and I'll just start the simulation. So we're going to have the control line here. If I reset it. Now initially none of them are chosen, but I'll put a value of 1 in here, and I'll put a value of 3 in here. So when the control line goes high, first thing it does is it chooses this one here. And then the next time the control line goes high, which we will determine from our microcode, it then chooses the remainder. And then we've got the remainder in there now. So it means that we can, on the first pulse in the microcode for this control, we can place the value div into R0, and in the next pulse in our microcode for this control line, we can place the remainder into R1. So that's how we do the division. So that's us finished this function. Let's go ahead in the next video and we'll see our next function. Goodbye.